But if you have more questions about stuff, just send me an email. Today we're talking about Chapter 5 and quadratic functions. So we previously talked about quadratic equations and told the whole story about how to solve them and all of that business. Now what we're going to talk about are quadratic functions. So basically functions derived from these quadratic expressions, and we're going to see that they give us parabolas, right? And what we're after here is essentially the same sort of thing that we did with lines. So let me give you an example. If I give you a line, a graph of a line, you should be able to then, from that line, write down an equation for that line. Or vice versa. If I give you an equation, right, you should be able to immediately write down the graph of that particular line. And it should be easy to go back and forth between the two. And there were many examples where we had to use that information in word problems. So, so there are many places where we needed to use that information in word problems. But now what we're after is the same sort of mechanism, but between parabolas, you know, sort of those U-shaped ones that we solve for something like x squared, and quadratic functions, right? So we should be able to go back and forth between the two. And it's a lot of stuff that we've already seen, but we're going to be giving it sort of names and solidifying it in a bit more detail. So what are the learning objectives for today? Well, they're the following. The first thing is that we're going to sort of introduce some vocabulary to describe some things that we've already seen in parabolas. And what this means in this first one is that you should be familiar with that terminology, right? So I'm going to give you sort of a picture here of the basic terminology and vocabulary associated to a parabola. And the nice thing is that if you have that information, if you can recognize what that information is, you can write down an equation for the parabola, okay? So we're going to talk about the characteristics of the parabola. And also you can graph it, right? So if you know what these characteristics are, they tell you the sort of the whole story about the parabola and the equation. And we're going to focus on how to go sort of back and forth. So understand how the graph of a parabola is related to the quadratic function. And along those lines, we're going to introduce two different formats. So we're going to call one the general form and one the standard form. And we're going to be really interested in going back and forth between those two formats, because one is easier for answering questions and the other is a little bit easier for like making computations. So we should be able to go back and forth between those. And then the last thing that we'll sort of talk about in today's class is the idea of a minimum and a maximum value, and that'll lead into some word problems. So in Infinity, in this section, there are 2 or 3 word problems at the end where we'll have to use some of these objectives that we've seen here to answer them. Okay, so I'm going to leave this up on the screen, and as soon as you feel comfortable with it, if you've taken it in your notes or you've read through it and you're okay, if you have a question you can ask, just give me a thumbs up, and when I see enough students of the 20 that are here, we'll go through and sort of move on. Okay, so it looks like a majority of the students are ready. So the first objective that I was mentioning was this idea of the various characteristics of a parabola. And what you're seeing here on the screen is just the general sort of graph of a parabola. This is one that's been shifted. It looks like we've been moved over to the right by 1 unit and down by 4 units. And the characteristics here will allow us to write down an equation, okay? So let's give some names to these things. The first thing that you should sort of see here when you're looking at this parabola is that there's a place where it turns, okay? So here it goes from decreasing to increasing. And we can also have parabolas that open downward, right? So this one's sort of opening upwards, but we can also have some that go downward. But even when they go downward, there's a place where they change from you know, increasing to decreasing or decreasing to increasing. And this turning point down here tells us a lot of information about the parabola itself and a lot of information about the equation. And this ordered pair, right, this place where we're turning is called the vertex. Okay, so we're going to give a name to it. Typically, we denote it by the ordered pair HK. Okay. So we'll typically give it sort of the ordered pair h and then k, all right? But that's called the vertex. And it's really the most important thing, right, of the parabola. It's like the thing that you really want to focus on, because once you know the vertex, you know a whole lot of information about this parabola. For example, you know the range, right? Because this one opens upward, and the y value of this vertex is 4. The range is 4 to infinity, okay? So the vertex is basically telling you that the range goes from that, vertex value, the y value there, and then anything above that. And if it was opening the opposite way downward, it would also tell you the same thing. It would tell you that that's sort of the ending point for the range. One other thing you should be aware of, and Affinity will ask you this a lot, and I think it may be a little bit confusing because there's not much work you need to do. The domain of these parabolas or these quadratics is all real numbers. You can always plug in any x value into these parabolas, into these equations for a parabola, and you'll get an output. So the domain is just negative infinity to infinity. But the range can be different. In this case, the range is from 4 up to infinity. So once you know the vertex, and if it opens up or down, you can write down the range and the domain really easily. Okay, so that point is called the vertex. The next thing that you should realize is that if you draw a vertical line, this dotted line here in red, if you draw a vertical line that goes through the vertex, then the parabola will be symmetric around that line. In other words, if I were to take this point here and mark this distance from this point to that line, thered be a corresponding point over here of the same distance away. And that's true for any point. Like this point up here is the same distance away from the red line as this point over here. Another way to think about it is if we reflected this parabola along the axis of symmetry, we would just get the same shape, okay? So it's symmetric around the axis of symmetry. And the axis of symmetry, right? So here we've got the axis of symmetry, is a vertical line. So the equation of a vertical line is x is equal to some constant. And it has to pass through the vertex. So it's always going to be of the form x is equal to h, right? Remember that this is the equation of a vertical line, right? Whatever the x value of the vertex is, h, you just set x equal to that particular value of h, and you get the axis of symmetry. Okay, so the vertex, its x value is telling you where you're symmetric about. Then we had our two intercepts, right? So there were x-intercepts and there were y-intercepts. Since a parabola is always going to be a function, there will be only one y-intercept, one and only one. And there will always be one because the domain is all real numbers. You can always plug in 0 into a parabola, okay? So there will be one and only one y-intercept for a parabola. On the other hand, there are potentially multiple x-intercepts, okay? And in this case, you can see there's one x-intercept here at x is equal to 3, y is equal to 0, and a second one over here at x is equal to -1, y is equal to 0. So it could also be the case that there are no x-intercepts at all, right? Maybe the graph doesn't hit the x-axis at all, and it could also be the case that for a parabola you intersect it at just one point, precisely at the vertex. But that's the only possibilities, right? For a parabola, you can have two x-intercepts, one x-intercept, or none at all. And this is really closely related to finding the solution to a quadratic equation because we saw the same thing sort of happening there. And I'll just give you a little bit of terminology here that's not on the picture. We also call these points here zeros, okay? But the difference is that we don't report them as an ordered pair. So here we would say that this parabola has a 0 at 3 and a 0 at -1, as opposed to an x-intercept at 3, 0 and an x-intercept at -1, 0. So the x-intercept is the ordered pair, and the 0 is just the x value that gives you back a value of 0, okay? So these are the pieces of information, these are the characteristics of a parabola that you need to know in order to graph it, right? If you know the axis of symmetry, you know the vertex, then you can just sort of get a pretty good sketch of the graph of a parabola. Now, the one thing that is not being sort of given to you here is sort of how much stretching and squeezing has been done on this parabola, right? And we don't really give a name to that in the terminology, but that's one other piece here that we have to be aware of, okay? So let's just go through and practice some of the details with this and make sure that we understand the terminology. And I'm going to ask you guys to respond in the chat with some of the answers to these questions. So the first thing that we'll look at here is what exactly is the vertex? So what do we have for the vertex in this case? Remember, the vertex is an ordered pair, and it's the place where the function turns. Okay, so remember the x value comes first, and then the y value. So here this is an x value of 3 and then a y value of 1. So right here, that vertex, in this case, as everybody pointed out, is at 3, 1. Okay? And you can see that basically it's been moved to the right by 3 units and up by 1 unit, right? I mean, we don't know quite what the sort of horizontal stretching and squeezing is, but we do know sort of what the vertical translation and horizontal translation is in terms of sort of moving to the left and right and up and down. Okay, so the next thing that you can get once you know the vertex is the axis of symmetry. And let's try to report the answer in the right format. Remember, it needs to be the equation of a line. So what is the equation or the axis of symmetry? Yeah, Eric, I'm going to assume that your plus was actually an equal. Yeah, so it's x equals 3, right? Whatever this value was here, the axis of symmetry it's just x equals the value of h, right? So that was our formula for the axis of symmetry. Before we hit the zeros, let's come back and talk about the y-intercept. So what is the y-intercept in this case? Remember, it's got to be an ordered pair. The y-intercept, if you remember, should have a y value, an x value of 0. Okay. And remember, the y-intercept is an ordered pair, right? So the y value right there at x equals 0 is, bam, right at 7, right? So 0, 7 is our y-intercept. The next one's a little bit tricky. It's not on the sort of list here. What are the x-intercepts? What do we have for an x-intercept in this case? So we've got a couple answers. Remember, the x-intercept is the place where the graph, that's that curve in blue, intersects or meets the x-axis. Yeah, and I think everybody's sort of getting it here that it can be tricky because there may not be any x-intercept, right? So the last one had 2 x-intercepts, this one doesn't have any. And what that means is that there's also no zeros at all, right? There's no place where this function has a y value of 0. Okay, 0 is just not in the range of this function. Notice that the range is 1 to infinity, right? 1 to infinity, and so 0 is not in the range here. And so there are no places where this function ever is equal to 0. And what this would mean is that if we were trying to solve for like the roots, like, you know, doing the factoring and all that sort of stuff, we would get a complex root for that equation. Okay, so again, that's just a little bit about vertex, axis of symmetry, the zeros. Remember, the zeros are not ordered pairs, right? Those would be given in terms of x values, but there's not any zeros in this case. Okay, so what I want to talk about now is the general form of a quadratic function and the standard form of a quadratic function. And I'm going to sort of do this on the board, and then we'll come back and talk about the rest of the details here, okay? So let me erase this picture, or this equation here, and start out with a function that we're sort of hopefully familiar with, y equals x squared. Right? And y equals x squared looks something like this. And what I would like to do is point out that the vertex of this function in this format is at 0, 0, because when I plug in 0 into this, I get 0, right? So what we can do is translate this, right? So we can move h units to the right and k units up, okay? So what I want to do is translate this thing h units to the right and k units up, right? And the picture will then look something like this. So I've moved it h units to the right, so right here will be h, and k units up. So this point will now be the point hk, okay? And over here, the formula would have been something like f of x is equal to x squared. What I want to do is write down a formula for this, okay? So here, if I want to move h units to the right, I do fx minus h, right? I plug into it x minus h. And the minus sign here is, again, because we're going to the right, okay? And then if I want to go k units up, I add k to the output, okay? So that's taking this formula here and moving it h units to the right and k units up. And I get this parabola there. So let's now go through and just evaluate this using function composition. Remember, f of x is x squared. So everywhere that I see x, I'm going to replace it with x minus h. And here I'll get x minus h squared plus k. Okay? And this is almost the standard form of our parabola. But like I said, this is just moving one type of parabola, of a parabola x squared. It could be a little more elaborate than this. We could be looking at something like ax squared, okay? And here, the a is going to be the stretching factor, right? The larger the value of a, the more compression there will be. The smaller the value of a, like if you get something like 0.000025, the wider the parabola will be, right? So I'm not going to indicate that here. That's why I didn't include any sort of unit. But we would have gotten here an ax squared there. And over here, it would be just a difference of an a, okay? So y equals a times x minus h squared plus k is the general form. I'm sorry, not the general form. It's called the standard form of a parabola. And notice that it depends only on the vertex and how much stretching or squeezing has been done. So once you know a, h, and k, you have the formula for the standard form of a parabola, okay? And if you give me any graph of a parabola, right, I could just read off what the h and the k are and then try and figure out the a, and then I could write down an equation. So we're sort of talking about, going back and forth. You can think about this as like sort of the point slope formula, but now for a quadratics, right? Okay, so now let me go ahead and talk a little bit about the slide again, and I'm going to erase what I have back here. I want to point out that we've been working primarily with this type of quadratic. This is called the general form. F of x is equal to ax squared plus bx plus c. And for a lot of questions where you're going to do like an application, right, like solving something in a physics course or something like this, they're going to give you the formula in the general form. Now, the standard form is much nicer in the sense that it tells you immediately where the vertex is, right? You can just immediately see the vertex is at hk. And it also tells you how much stretching and squeezing has been done, right? If the a is positive, it means the parabola is going to go up. If the a is negative, it means it's going to go down. And the magnitude of the a is telling you how much stretching or squeezing has been done. So we would like to be able to go between these two. And the first thing I'll tell you is that the a's are the same. So this is really nice, right? If you want to go from the general form to the standard form, the A's just stay the same. But what I'd like to do now is derive these two equations for you, right? They look pretty complicated, but they're actually really easy to use. And the purpose of these equations is that if you give me something in the general form, if you tell me A, B, and C, then you can use these two equations to compute H and to compute K. And remember, H and K are the vertex. So once you know that H and K, you almost have the standard form. Okay, but let me go ahead and derive where those two formulas come from, okay? Just so it's clear. So the general form is this, and the standard form looks like this. And if they're going to be the same, they're going to have the same graph, they should be equal to each other. And what I'm going to be after here is trying to solve for H. Right? I want to figure out what H is on its own, and then we'll figure out K after that. Okay? But I want to figure out what H is. And we can do it by FOILing out this side. Okay? So let's multiply that side out. We're going to get A, and then FOIL this out. We get x squared minus 2xh plus h squared. And then we still have the plus k. On this side over here, we still have ax squared plus bx plus c. Okay. Now what I'm going to do is distribute the A. So here I get ax squared minus 2axh plus ah squared, and then plus k. And notice I don't put an A next to the k because it wasn't included in the inside of the parentheses. So just add an A there, add an A there, and add an A there. And this is still equal to ax squared plus bx plus c. Okay, so normally I would start like solving for h or something, but instead this time what I want you to focus on is the terms that have an x, just x, right? So this term has an x squared, so we're not going to look at it. This term doesn't have an x, so we're not going to look at it. The only term I want you to focus on the left-hand side is this, b times x. And on the right-hand side, this term has an x squared, so we don't need to look at it. This term doesn't have an x, so we're not going to look at it. And this term doesn't have an x, so we're not going to look at it. But this term here does. So this is the coefficient of x, and this is also the coefficient of x, and we can put the two of them together. Okay? So here we get bx is equal to negative 2a xh. And the only way, again, that these two parabolas are going to be equal to each other is if the terms that have x's are the same. Okay? If they were different, they would be different parabolas altogether. So what we can do here is you'll notice there's an x on this side and an x on that side. So let's just divide by that x. We're assuming x is not 0. But we'll divide by that x, and we'll get b is equal to negative 2ah. And then from there, I can divide by negative 2a, and I get h is equal to b over negative 2a. And I'm going to box this because I want to point out that this is exactly how you'll figure out h if you're given a, b, and c, right? If you're given a, b, and c, you identify the a and the b, and you compute b over negative 2a, and that tells you the x value of the vertex. It also tells you the axis of symmetry, right? Because now we know that x is equal to this b over negative 2a is exactly the symmetry point of this guy. Okay, so now the question is, how do we find k, all right? So we now know how to find h directly from this formula. And notice it's not something that's unfamiliar, right? If you remember studying for completing the square, this is the term that you needed to complete the square, right? Negative b over 2a was exactly the term for completing the square. Okay, so let's just go back. And again, the formula was a times x minus h squared plus k. And I want to point out the following. If I evaluate this thing at h, at the vertex, okay, then what do I get for my output? Well, it's going to be h minus h squared plus k. That's going to be a times 0 squared plus k. So 0 squared is just 0. A times 0, that's just 0. And 0 plus k is just k. So to figure out k, all you've got to do is plug in h, Well, what was h? It was b over negative 2a. So now you can find a formula for k. K is just going to be f of b over negative 2a. So again, you just plug in this value of h that you got in the first step back into the original function that you were given, and bam, you get back out k. And the point, again, hk is the vertex. Okay. So this negative b over 2a is telling you the x value of the vertex, and then you plug it in, you get the y value. And that's exactly what is being said here, right? So the h is negative b over 2a, and the k is evaluating the function at negative b over 2a. Let's go through and do some examples of this sort of thing, okay? So how are we going to convert from sort of the general form to the standard form? Before I do that, I should mention that going from the standard form back to the general form is really easy. You just multiply everything out and write the powers in decreasing order, right? So you just simplify the quadratic as much as possible to get back to general form. But going from general form over to the standard form is a little bit harder. So let's go through an example of that. So here we'd like to find the standard form of f of x is equal to x squared plus 6x minus 2. And the first step is just to figure out your a, your b, and your c. Okay, just like you did for the quadratic formula. And to get the h, you just compute negative b over 2a. Then notice I moved the negative sign up from the denominator up to the top. The negative doesn't matter where you put it. You could put it in the numerator and the denominator, or just out in the front. They're all equal to the same thing, right? So here I'll just put it next to the b and write it as negative b over 2a. And then remember the k is f of negative b over 2a. So let's do this computation first. And those of you that are following along in the chat, tell me what you get for your value of h. I think Isaiah's already posted. Okay. So yeah, the h here is going to be negative 3 because it's negative 6 over 2 times 1. Okay? And 6 divided by 2 is 3. So there we immediately know that the h is negative 3. And we don't even have to do the computation again. All we have to do is f of negative 3 now. Okay? So what do we do for that? Well, we go back to the function that we were given. It's going to be negative 3 squared plus 6 times negative 3 minus 2. Okay, and then again in the chat, once you get this one, what do we get for that value of k? So we want to square this guy, add it to this. Okay, there we go. So type it in a calculator or just multiply it out, and you should get negative 11, like everybody else is getting here. And again, I just wanted to give you a moment to try it out on your own. You just plug it right back into the function you were given. Okay, so remember the standard form, right? The standard form is this a times x minus h squared plus k. And remember, the a is the same in either form, the general form or the standard form. The a is exactly the same. So here, we could rewrite this f of x. It's going to be a is 1, so I'm just going to leave it off. X minus the h is negative 3, so minus the negative 3 is plus 3. And then the square, right? So that's that square on the top, and then plus whatever the value of k was, which was negative 11. So if I add negative 11, it's subtracting 11. Okay, and so here is the standard form of this parabola. And you could have also gotten this by completing the square. Okay, you'll just notice we're sort of doing this just graphically here, but we could have also gotten this answer here by going back and completing the square. But now we know pretty nicely here that the vertex here is negative 3, negative 11, right? So it's sort of a parabola that's been moved 3 units to the left and then 11 units down. Okay, so that's going one direction, right? And from this information, we could write down a lot of stuff, right? We could write down the axis of symmetry, we could write down the vertex, we could write down the range if we would like. Let's actually do that here, just so we can get, again, a better sense of what we want. So here's the domain, and then here's going to be the range. The range is the harder one. What's the domain in this case? The same for every possible quadratic. What do we get for the domain? All real numbers, right? Negative infinity to infinity in interval form. However, on the range, we need to think about the k value, right? So the k value here was negative 11. And you'll notice that the a is positive. So this is a parabola that sort of opens upward, right? I drew that wrong. The vertex should be down at somewhere over here. It opens upward, okay, because the a is positive, but the k value here of the vertex is at negative 11. So what's the range? It's going to include from some value all the way out to infinity. What's that starting value? Yeah, negative 11, right? So the k is really telling you either the starting point or the ending point of the range, right? It would be the ending point if we would have had a negative a here. Okay, so you can immediately tell domain and range pretty quickly from this sort of thing as well. Okay, so let's just come back here and talk a little bit about how we would go from, so this last example we did was how to take the general form and put it in standard form. But now what we'd like to do is the following. You give me a graph of a parabola, put it into standard form. And it's pretty straightforward. Once you have the graph, you'll know the vertex. So you'll be able to identify h and k immediately, and that's your first step. Then your next step is to put it in standard form. So f of x is equal to a times x minus h squared plus k. So again, this is given the graph. We want to write down the formula. The only thing that you won't know is the a, right? At this point, the only unknown should be the a, because you'll know the h, you'll know the k. So the only unknown is a. And this is where you'll need a second point on the parabola. So you'll need to find something other than the vertex. And this is like if you wanted to write down the equation of a line, you would need at least two different points on the line, right? So here you need the vertex, and then in addition, you need a second point that's somewhere on this parabola. So once you have that second point, you'll plug it into the formula, and I'll give you an example of this, and it'll allow you to figure out what a is. Once you know what a is, you just plug it back in and you're done, right? And then here they're saying they want it back in general form, so if you want it in general form, you have to multiply everything out. Remember, this is the standard form. General form just means multiply it out and write it in decreasing terms. Okay, and I'm just going to go through and do an example of this here. So here we have our nice parabola. We should recognize that the a is going to be positive because it's opening up. We can see that the range is from -3 out to infinity, including -3. The domain is all real numbers. And we can identify the vertex. So in the chat, what is the ordered pair here for this vertex? Yeah, so the x value is -2, and the y value is -3. So it's -2, -3. And that immediately tells you the h is -2 and the k is -3. Okay? So we're almost basically done with the standard form, right? Because remember the standard form here, let me go ahead and jump to the full screen, is f of x is equal to a times x minus h squared plus k. And now we know what the h is. H here is -2, so it's going to be x minus -2 or x plus 2. And then k is -3, so That's going to be minus a 3. And again, the only unknown at this step is the a. So now we'll need a second point on our parabola, right? So here we need a second point on the parabola. And you can use any point that you would like. But in order to just keep things a little easier in the chat, I'm going to ask you, what is the ordered pair for the y-intercept, right? Because the y-intercept is another point that's on this graph. So yeah, the x value here of the y-intercept is 0, and the y value is at -1. So a second point on the graph, and again, we could have used this point over here, right? I mean, it doesn't matter what point you pick, you just have to pick some point on the graph. But I'm going to pick that point over there at 0, -1. So we need a second point on the parabola, 0, -1, the y-intercept. And what you'll do with this information is you'll use it to figure out what a is. So remember, this is the x value, and this is the y value. F of x is the y value, so this is the same thing as saying -1 is equal to a. The x is again 0 plus 2 squared, and then -3. And you'll now notice that the only thing that's unknown here is the a. So once I plug in the value of x and y at this other point, then the a is the only unknown. Okay, so let's go ahead and solve this. So here I'm going to move the 3 over to the other side. So that's -1 plus 3 is equal to 0 plus 2 is 2, and 2 squared is 4. So that's going to be 4 times a. And over here on this side, 3 minus 1 is 2. So this is 2 is equal to 4a. And then we'll divide both sides by 4, and we get a is equal to 2 over 4. In other words, a is 1/2. Okay, so here we've got a is equal to 1/2, and that was the only other piece of information that we needed, okay? Because now the standard form is going to just be 1/2 x plus 2 squared minus 3, right? That's the standard form. So this is standard form. And it's enough information to give you the equation of this parabola. However, in a lot of instances, it'll ask you for the general form. And if you wanted to get the general form, you would just multiply this whole thing out. So be careful in Affinity what they're asking you to do. They may be asking you to look at the general form. Okay, so that's how you go from the graph directly to the equation, right? And again, if you have the equation here, it's pretty easy to go back to the graph. You just pick the vertex. You can graph the y-intercept, and then that'll tell you if you're sort of opening up or down, and you can sketch your graph from there. So we're sort of now seeing that back and forth. Let's do an example, you know, sort of similar to what you might have seen for lines. You know, a lot of the times they don't give you the graph, they just give you information about the graph. And so here's an example of that, right? Here they're asking you to find the equation. And I think, again, here it's in general form. So you should multiply it all out, but I'm just going to do it in standard form and leave that for you guys to do. And they tell us that the vertex is at 4, 4, and it passes through the point -129. So we can just go through that process that we just did, right? So here, we know immediately that f of x is a times x minus the h. In this case, the h was just 4, and the k is also 4, right? Because, again, it's just the ordered pair 4, 4 for the vertex. Now, what we don't know is this scaling factor, right? We don't know if it's opening up yet or opening down and how wide or narrow it is, okay? So now what we can do is take this second point and plug it in and figure out what the a is, right? The a is the only unknown. So here, the x value is -1, and the y value is 29. So this is the y value. And there's x, so -1. And now we just solve for the a. So I'm going to subtract 4 from both sides. I get 25 is equal to a times -5 squared. And -1 minus 4 is -5. So that's 25 is equal to a times 25. In other words, 25a. And then I divide by 25 on both sides, and I get 1 is equal to a. So now I can just write down the answer here. It's just going to be, this is a 1, so I don't even write it there. I can write this as x minus 4 squared plus 4. Okay, and now we can see that it does indeed open upward, and there's no scaling factor at all, right? It's just a scaling factor of 1, so it looks just like x squared. Just moved over 4 units and then up 4 units. Okay, so be prepared to just be given information about the graph and then be able to write it down. Now, I should mention here that I'm not going to box this answer because this isn't the general form. This is the standard form. If I wanted the general form, I'd need to FOIL this out and collect like terms. Okay, so be a bit careful in Affinity what they're asking you about. Okay, so just one more time, domain and range. So here, I want to point out again that if you have it in standard form, then you can immediately write down the domain and range. The domain is easy. The domain for every quadratic is negative infinity to infinity. Okay, you can plug anything into that formula. The range is a bit different. Remember, the range is going to be one of two different formats. It's either going to be negative infinity up to k, or it's going to be k up to infinity. This is if a is negative, because it'll be opening downward, and this is if a is positive, because it'll be opening upward. So in this case, is this thing opening upward or downward? What do we have? Is it a parabola that's going up or a parabola going down? It's going to be upward, right? It's going to open upward. And it's going to be opening upward because it's positive. Yeah, so open, like I'm sort of, where's the cup pointing, right? Pointing up. Okay, and the k value, right, is telling you where it starts or where it ends, where the range starts or ends. So here in this case, it's 8 over 11. So because the a was positive, it's 8 over 11 for the starting point, and it goes all the way out to infinity. So the range is just 8 over 11 all the way out to infinity, including 8 over 11. So really all you need to know is what's going on with that k value, and then whether or not this thing is positive or negative, if it's opening upward or opening downward. Okay, so that tells you the whole story about domain and range. And I want to point out something here in terms of some of the applications. So for a lot of these word problems, and I think there's like 2 or 3 of them at the end in Affinity, they're going to ask you to find the maximum or minimum value of some quantity. And it turns out the quantity can be described by a parabola. Now, if the parabola opens upward, in other words, if the a is positive, then the k value is a minimum. Okay. If the parabola opens downward, meaning the a value is negative, so in this case it would be -1, then the vertex here corresponds to a maximum. And we say that the y value is the maximum or the minimum, the extrema, and the place where it occurs is the x value, right? So for example, this maximum occurs at an x value of -3, and the maximum value is 4. This here has a minimum value of 1, and that minimum value occurs at 2. Okay, and for a lot of questions, they're going to be asking you sort of what's the minimum or what's the maximum value. So let me, in the last 5 minutes, give you an example of that. And again, I'll just point out that the k value is going to be the min or the max, and the h value is going to be the location of the min or the max. And whether or not it's a min or a max is determined by if a is positive or if a is negative. Okay, so here's a typical example of a problem where you may need to use the min or max. Here you throw a ball off of a building, right? So you imagine you're on top of a building and you throw the ball. And it turns out that according to physics, the ball will follow a parabola. Right? Take a physics class if you want to know the details of why it follows a parabola. But here, we're going to use the fact that it does follow this parabola. And the formula that we get for that parabola is the following. So h of t is the height above the ground as a function of time. So you tell me the time that's passed, and this formula will tell you how high above the ground you are, okay? And it's a parabola, and it's opening downward. So again, it looks, something like this, right? So this maximum value here is going to tell you the maximum height. And again, it's something like this, right? So here's the t-axis, and here's h of t over here on the y-axis. And this ordered pair, again, is that ordered pair hk. This is going to be the value where the height is maximized, right? And what was it? It was the x value of the vertex, okay? So this is like a super simple problem. You just need the x value of the vertex. For this formula, the b is equal to 25, and the a is equal to negative 4.9. Okay, so let me come back here. So that's my a and my b. So then remember the h here appears at negative b over 2a. So the b is 25, negative 25 over 2 times the a is negative 4.9. And so you can plug that info directly into a calculator, and what you end up with is that x value of, or t value in this case, of 2.551. And this is in terms of seconds. And why is it in seconds? Well, it's the along the t-axis, right? So this is telling you exactly the value of t that maximizes the height. And all you have to do is compute the x value of the vertex, the line of symmetry. Okay? So that's the same sort of thing. And then one last question here that shows up in Infinity is this question about the dimensions of a rectangular corral. But I think we're a little bit out of time here if we want to stop class directly at 11:50. So I'll leave this one for you guys to ask about on our Monday Q&A if you need help with it. But it's, again, another example where you have to come up with a quadratic and then compute the vertex to answer the question. And notice that if you wanted the maximum or the minimum value, you would just compute the k value, right? And that would tell you exactly what the max or the min was. Okay, I'm going to go ahead and stop there and tell you guys thank you for being here. And I'll be around for the next 10 minutes or so if you have a question or